This video will be about the spatial reference system in fluid dynamics. The idea is, this video will be about the spatial reference system in fluid dynamics. The idea is to define a reference for the observer position. So where the observer is, how it moves, and how it is in relation to the physical quantities and the movement of the physical field. There are more or less three possibilities about the observer configuration. The first is in a Lagrangian reference frame. The observer monitors a trajectory in space of each material point and measures its physical quantities. This is very abstract, but we will look at it in detail. This means that the Lagrangian reference frame is, if you have a material point, the observer is fixed with this material point. So if the material point moves or deforms, the observer will move with this material point. This is more or less what this sentence says. In the Eulerian reference frame, in which the observer monitors a single point in space when measuring a physical quantity, the measuring probe stays at a fixed position in space. This means if a physical field or a kind of a beam is deforming, we'll look at the deforming beam from a fixed location on. If we would be in a Lagrangian system, we would move with the beam, with the material points on the beam. There is indeed a third possibility. It's called arbitrary Lagrangian Eulerian frame of reference. There the observer itself monitors a physical quantity while moving with defined velocity. This means that the observer is not fixed in space, and it also does not move definitely with the material point. It moves with some intermediate velocity, and this is for instance used when we are calculating rotating machinery. There people often use the arbitrary Lagrangian Eulerian reference frame to kind of track the movement of the rotors. So in the sense, these are different reference frames as depicted here. We have the Lagrangian, the Eulerian, and the ALE, so the arbitrary Lagrangian Eulerian system. And between these systems we have defined different mappings, and based on these mappings we can also define some continuum properties like the deformation gradient and stuff like this. So these reference frames are very powerful tools, and we look at it in detail. What does it mean for the material derivative? We learned what the material derivative was already before, and so we look at the consequences on the substantial derivative, so the material derivative, which is written down here. It consists of a partial change in time plus a convective change with the gradient. And for the Lagrangian frame of reference, it means that we move with a material point, that we already sit on the material point. It means that the substantial derivative itself is equal to the partial change in time. So if we are in the Lagrangian reference frame, then we are more or less fixed and have just a simple partial change. In the Eulerian reference frame we have the following thing. There we also have the local change, but as we are at the fixed location, there can occur convection of the physical quantity. So the change we see is not only the local variation, there also can be convected some change in itself, and this convection is expressed by the second term. In an arbitrary Lagrangian Eulerian reference frame, it's very similar to the Eulerian, but indeed we have a convective velocity, which may be a grid velocity or a velocity which is the difference between the movement of the observer position and the convection velocity. And this is how in an arbitrary Lagrangian Eulerian reference frame the convection is depicted. So these are these three reference frames, and yeah, they are useful for calculation, and usually they are applied in different disciplines in continuum theory, for instance in calculating mechanical displacement. People often use the Lagrangian reference frame. Doing fluid dynamics, people often use the Eulerian reference frame, as I said, and in kind of modeling rotating machinery, people often use the Yale formulation. Yeah, and that's basically it on the spatial reference systems. If you have any question, you can just simply ask me in the blog below the video. And yeah, that's it. And I'm happy if you watch the next video about the Reynolds transportation theorem. Thank you.